Perfect. So it's my great pleasure to introduce Pierre-Alexandre Mattei from INRIA. And he's also affiliated with the Mathematics Research Department at the University Côte d'Azur. He's also the chairholder and deputy scientific director of the 3IA Côte d'Azur. So we're very excited to have him speak today on ensembles in machine learning, simple theory, and simple practice. Take it away, Pierre-Alexandre.
Okay, yes, many thanks for the invitation. I've watched a few videos of this seminar on YouTube, and I'm very honored to be there. So many thanks, Ricardo and George. And yes, so this is going to be about some work on, but this is going to be about ensembles, and most of the talk are going to be about relatively simple things. Many of them are not new. Uh, but some of them are the subject of ongoing work. In particular, with Rafael Razafadra-Lobo, who's a PhD student of mine, and also Damien Garot, who's a professor in Würzburg, and Rémi Sen and Frédéric Precioso, who are also at Université Côte d'Azur and INRIA. And part of this work has been published in this paper, Ensemble Getting Better All the Time, which it's actually not an archive paper anymore. It was published in JMLR. And yeah, and there are also like preprints from Raphael on diffusion models that I will mention, but that I don't really talk about in the slides. Okay, so what's the menu for today? So I want to start with a basic historical intro on ensembles. And then I want to kind of motivate the sort of questions I'm going to ask theoretically in this talk by looking at some ensembles that are used in practice a lot, in particular dropouts and ensembles. And then after this motivation, we're going to actually look at those questions theoretically. And the question that the main question I'm going to look at is it worth doing ensembling? And in particular, is it worth ensembling many models? And in particular, is it worth ensembling is assembling K models better than ensembling K-1 models? So okay, so let's start. So I'm going to start with a very brief intro about like the history of ensembling. So the idea of ensembles is essentially the idea of collective intelligence. We have several base models, and we hope that collectively they will perform better than individually. And so this can be used in pretty much any sort of machine learning task. So the main application is classification, of course, but we can also use ensembles for regression or for density estimation. So here you have a basic example that I'm going to use several times today about ensembles for classification. So we have a single network that is trained to classify ensembles of skin lesions. So in that case, it's just a mole, so it's a benign lesion. And essentially, we pass the mole through the same network, but with different dropout masks. And the fact that we have different dropout masks gives us different outputs. Okay, so here, like we have the output is the probability that it's a cancer, or I guess more mole than the cancer because they are higher than 50%. And so those three different dropout masks give us three different probabilities of cancer, of non-cancer. And then the idea of ensembling is to say, okay, so to average those three probabilities to get an aggregated model that will hopefully be better than the individual models. And in that case, it's just averaging the probabilities. And of course, we could also do that for regression. We could just also average the outputs of the regression networks, or for density estimation, we could average the densities. So the trend, so this idea of course, collective intelligence is very old. You can find this in like old philosophy textbooks. But in machine learning specifically, it became quite trendy in the 90s, in particular through the work of Leo Breiman, who came up both with bagging and with random forest, which is essentially a combination of bagging and decision trees. And so the the basic example of bagging was simply to start with a good base model, like for instance a decision tree or a neural net, and to train this model on different subsamples of the data, and those subsamples are bootstrap samples. And then after training, we can aggregate the models. So hence the name bagging for bootstrap aggregation. So we aggregate those different bootstrap models, and we get an average exactly like what we did for Dropout in the previous slide. But Brayman in particular applied that to decision trees, which led to random forests, which are still one of the state-of-the-art algorithms in machine learning, and have been extremely popular. And so this trend for decision trees in particular, this trend was quite heavy in the 90s, but it was also quite heavy for neural nets. And the idea here was very simple. There was this idea of, okay, so since neural net training is very stochastic because of stochastic gradient descent, and also because of the non-convexity of the loss, well, if we train the same model with different starting points, different initializations, we will get different results, and we can average those results to get an ensemble. And this idea was in particular quite developed in the paper by Lars Kristiansen and Peter Salomon in 1990, where they use this idea of averaging different the same network but trained with different initializations. And this was a very influential paper. And that led to several follow-ups and several works in the 90s. So this was the 90s, and again, ensembles were super popular back then, but they are still popular today. And in particular, for tabular data, the ensembles of decision trees are still pretty much state of the art. They are either very close to neural nets or actually sometimes even better for small data sets. There was this paper by people from INRIA Paris, INRIA Saclay a few years ago about this. And like it was 2022, now it's 2026. The neural nets are a bit better now, but still, I think ensembles of decision trees are still extremely tough baselines for the tabular data. So yeah, ensembles of decision trees are still extremely popular, and so are ensembles of neural networks. And essentially, it was through two examples. The first example is an example I mentioned already, which is Monte Carlo dropout, and it's a very simple idea where you use different dropout masks, and then you average the outputs of the different networks that correspond to the different dropout masks. The very nice thing about this is that it doesn't cost much, because essentially it's you just train a single time using dropouts, and then after training you average your dropout masks. So it's very cheap, and it works quite well. It was actually already suggested by the famous paper, the famous dropout paper by Srivanava, Hinton, and others. And it was mostly popularized by paper by Yaringal and Yuzun Karamani, published at ICML in 2016. So yeah, Monte Carlo dropout is the first big avenue of ensembling for neural nets, but there is another big one, which is actually the one I've already mentioned. It's this idea of training with different initializations, and this was essentially rebranded as something called deep ensembles a few years ago. But in a very influential paper called just deep ensembles by Balaji Lakshminarayan from DeepNight. And an important thing about essentially all of those results is that essentially, if you look at those papers, in particular the recent papers about Monte Carlo dropout or deep ensembles, a big insight is that experimentally ensembles work very well if we look at uncertainty-aware metrics. And by uncertainty-aware metrics, I mean metrics like the cross entropy that actually looks at the probabilities, or the Breyer score, like scoring rules in general. But if you look at metrics that don't care about the uncertainties, like the accuracy, for instance, or the AUC, essentially ensembling is usually worth it, but there is clear, there is a very, the story is much less obvious. And there are some cases where ensembling can actually hurt. And this is something that we're going to look at today. Okay, so my history of ensembling was very ML oriented because I'm a machine learning researcher, and this is a machine learning seminar. But of course, this idea of collective intelligence is very old, and I do want to mention that it goes way beyond ML, and already in the in the 18th century, so Condorcet proposed a mathematical formalization of this idea of collective intelligence. And actually, a thing that I find quite interesting is that some of the very technical points of this mathematical formalization will actually be useful today. So and they are very, very non-trivial. So yeah, so there is actually a counterexample that is in this book that will be a counterexample in a theorem that we'll see later. So it's so those results are actually quite subtle and quite mathematically complex. And in many other fields, people have looked at this idea of collective intelligence, both from theoretical and practical perspectives, econometrics, and also, of course, political science, because it's tied to the idea of democracy, psychology, like many other fields. And often this idea of collective intelligence is summarized by this phrase, wisdom of crowds, that was popularized by this book that was extremely popular. So it's like a popular science book that was by James Surowiecki, which was very, very popular. And yeah, this phrase, wisdom of crowds, was used in many papers, both in machine learning and outside, just to, again, as another way to talk about collective intelligence. Okay, so that was the introduction. So now let's look at what sort of things we're going to look at today precisely. We are going to study ensembles in a fairly general setting. We're going to study ensembles that are slight variations of the same model. And this is going to be very general because it will, for instance, include random forests, which are, again, slight variation of the same decision tree, but trained on different subsamples. Deep ensembles that are slight variation of the same neural net, but trained with different initializations. Monte Carlo dropout, which are actually the same neural net, but with different dropout masks. Bagging, same thing as random forests. Could also include test segmentations, where you have the same network but different inputs. So it's a very, very general setting. Even though it's a very, very general setting, it's not a setting that includes everything. And there are some examples that do not satisfy this criterion. And essentially, it's all the examples where the ensembles are, the members of the ensembles are done iteratively. So for instance, in boosting, we create the members of the ensembles iteratively. In Bayesian model averaging, the ensemble members are quite different because they can be very, very different models, and they can be they are not typically not slight variations of the same model. They can be, but typically they are not. And also the sort of ensembles that are used in weather forecasting, it's not all of them can be seen under the lens above. So yeah, so just to be very clear about what we're going to do today, we're going to look at ensembles that are slight variations of the same model. And of course, I'm going to be more mathematically precise later. But maybe advertisements. So if a very good book about ensembles is this book by Ludmila Koncheva that I found very, very enlightening. It's already 10 years old, but I think it aged quite well. Of course, there is not much about ensembles of neural nets, but for the rest, it's very, very good. Okay, so let's look at basic but popular ensembles of neural nets to elaborate on the examples I mentioned before. So again, so deep ensembles, we have different neural nets trained on the same data sets, but with different initializations. And it's somewhat related to Bayesian deep learning because you could see that those different training has some different rows of the same posterior. Monte Carlo dropout, I've mentioned it already. It's like the same network, the same train network, but with different masks. So here, for instance, you have one mask on a small MLP, like a different mask, and of course, those different, even though the weights are the same, since the masks are different, at the end, the output is going to be different. And again, there is some relationship with Bayesian inference. And there have been many papers on the subject, but I think a good paper that summarizes this is this paper by Ron, Matthews, and Garamani that was published at ICML in 2023. And essentially, yeah, I wanted to mention those models, those examples, because I'm going to mostly use those in my experiments. Yeah, so and mostly actually Monte Carlo dropout because it's fairly cheap. Okay, so now let's turn to the real research question of the talk: when and why ensembles work. So before we start doing math, I want to start with some empirics. And okay, so let's go back to the example I started with, which was predicting if something is a mole or a melanoma using Monte Carlo dropout. So here of course the real network is not this very small network. It's a convolutional neural network. It's something a bit bigger, but again, the principle is the same. My input is the image of a skin lesion, and I pass it through 3 different versions of my dropout network, and at the end, I average the probabilities to get a final prediction. And in that case, and of course, I want to compare my final prediction to the actual true diagnosis, which in that case was not the cancer. Okay. All right. So one example, extremely important in this study is going to be the so-called infinite ensemble. That will be essentially what would happen if I were to ensemble an infinite number of models. So in that case, so my models are just different rows of dropout masks. So it's fairly clear what's the uncertainty, what's the randomness of my ensemble, and essentially this ensemble is just the average over this randomness. And this is exactly what would happen if I were to ensemble a very large number of dropout masks. Of course, this is impractical. So in my curves, when I talk about the infinite ensemble, I will talk about what happens when k is like I think I think it was 1,000 in the experiments. So 1,000 is going to be my version of the infinite. But yes, so this object is going to be very important, okay? Because this object will essentially say, would ensemble be worth it if I had like an infinite amount of computational power? And in Monte Carlo dropout, it's fairly easy to compute that for 10,000 dropout masks because it's just every 10,000 forward pass through the same network. But for deep ensembles, it's much more expensive because that would require to train 10,000 models, which is of course more complex. Okay, so what's going on if I do this on this dermatology data set? What's going on? Well, if I look at the cross entropy as a function of the size of the ensemble, well, everything looks great, right? The cross entropy goes down. We do win a few points of cross entropy, and clearly, like an ensemble, like the ensemble is getting better and better, and yeah, it makes sense to do an ensemble as big as we can. Okay, so very nice. And again, if you look at curves in ensembles papers, often they will look at more they will more look at the cross entropy than as the accuracy. And indeed, if we look at the accuracy, the picture is a bit less clean. So it goes up, which is nice, of course, and then it's kind of plateaued, but the plateau is not super clear. So perhaps it's even going down. It's not really clear. And one thing that is kind of interesting is that we can elaborate a lot about this curve. And so again, so what are those first observations? So for the cross entropy, ensembles are really monotonically improving and getting better all the time. That's great. But for the accuracy, things are really less clear. And okay, so if we investigate, we can notice that it's possible to actually split our test data set. So here, all of this is on the test data set. We can split our test data set into 2 parts. One part where the accuracy goes up, always, essentially, or on average at least, and one part where the accuracy goes down. Okay, so if we do the splits, we can actually have to write this this kind of weird curve. We can write it as a sum of one curve that is increasing and one curve that is decreasing. And okay, so here my split was quite simple. It was on the left, we have images where the asymptotic prediction, the prediction of the infinite ensemble, is right, in the sense that it gives the correct label. And on the right, we have images where the asymptotic prediction is wrong, in the sense that it gives the wrong label. And here it's really just a binary classification. Okay, so that's good. And of course, it makes a lot of sense because, I mean, if we know that the infinite ensemble gives the right label, we know that this accuracy will converge to 100% because for all those images are the images where the infinite ensemble is right. So at infinity, we will converge to 100%. And on the right, those images are the images where the infinite ensemble is wrong. So at infinity, it will converge to 0%. So all of this makes a lot of sense. What I find a bit weird, though, is that if we do the same for the cross entropy, of course, for the correctly classified images, the loss goes down, as exactly like for the accuracy. The accuracy gets better, and here the cross entropy gets better. What is quite weird, though, is that for the cross entropy, even for the images where the infinite ensemble is wrong, the cross entropy gets down. So the cross entropy is always getting better. Okay. So here we really have like a very big contrast where the accuracy, the cross entropy is always getting better in all cases, even when the model is really bad. And of course, the scales of the two curves are quite different, right? The correctly classified images, the cross entropy is quite good, and the incorrectly classified images, the cross entropy is quite bad. But even though it's bad, it's still going down. So, like, if we look at this very, very quickly and without too much care, we could say, oh, ensembling is great. And of course, if we do the same here, clearly ensembling is great on the left, but it's really bad on the right. So okay, so here we have a clear difference between the behavior of the cross entropy and the accuracy. And okay, so this was a single example, but it turns out that this is a very, very universal behavior. And in particular, there was a very great paper by Nicolas Probst and Eleanor Boulestex that was published in JMLR in 2018. And it was a paper that mostly looked at random forests, and essentially they look at a lot of data sets, like more than 300. And their conclusion was pretty much similar to what I just described. The empirical conclusions were that if you just look at the cross entropy and also the Breyer score, well, ensembles are always getting better all the time. So all the curves are just monotonic in the right direction, and you're like, okay, ensembling is great. On the other hand, if you look at other metrics like the accuracy or the AUC, well, the behavior is more subtle. And for some data sets, you can even have like some non-monotonicity, and you can have like ensembling that hurts. And essentially, we're going to revisit those conclusions theoretically today. And yeah, so this is going to be the main challenge for today. Okay, so in what way? Okay, so here we have a stark difference between cross entropy and Breyer score on the one hand, and classification error and AUC on the other hand. So big question is there a big difference between those of losses? And so usually I ask the question to the audience, but since it's a virtual talk here, I'm going to ask the question to myself. So what's the difference between cross entropy and Breyer on the one hand and classification and AUC on the other hand? Well, there are many differences, but one of them is that cross entropy and Breyer are convex, and classification error and AUC are not. Okay, and this is going to be the key point today. We are going to see that this convexity divide is really responsible for the results that we just showed. And essentially, what we're going to show is that for convex losses, ensembles are always getting better. They're getting better all the time. on the other hand, for non-convex losses, ensembles will be improving for good data points, essentially the good images that we saw before, the images where the asymptotic model was right. And they're going to get worse for bad data points. Okay, so really we're going to show that this the behavior we just saw and the behavior that was witnessed by Probst and Boulez-Sex in their 300 plus data sets is very universal and actually fairly easy to understand theoretically. Okay, so my examples were for classification. I want to say that this goes way beyond classification. So every time we have like an ensemble and a loss function, this is going to be true. And the main important question is going to be the convexity of the loss, regardless of the task, classification, density estimation, regression, whatever. And even tasks that have nothing to do with machine learning, and for instance, like just collective intelligence. And this is an example of such a task. Here, this is predicting the ratings of upcoming movies, where we ask people, we ask a crowd to say, okay, so just watch a trailer, let's say the trailer of John Wick 2, and try to predict before, of course, the movie was out, and try to predict the rating that the movie will get on Rotten Tomatoes. And as we can see, so here I'm showing that for 3 movies and an ensembles of people who try to predict the rating. And if we look at just the squared error, so again, this has nothing to do with machine learning because the models, in a way, are not models but humans. So if we look at the squared error that is convex, for all 3 movies, the losses are going down. But here you have 2 examples of non-convex losses that are essentially non-convex losses used in robust regression. And for those non-convex losses, well, we can see that there is one movie where the loss is going up, another one where it's actually also going up or perhaps plateauing, and another one where it's going down. And again, we have the same divide between convexity and non-convexity in this context. So yeah, so my point is that really, of course, I'm mostly going to talk about machine learning, but this is essentially the math are true for pretty much any sort of context where we aggregate models and we have a loss function. Okay, so let me just look at the time. Okay.
You have about 20
okay,
more minutes.
I still have
about 20 more minutes.
Okay, thanks, great. Okay, so yes, so let's start with so again, we have 2 different worlds. The convex one where everything works great, and the non-convex world where everything is more complex. So let's start with the convex world. And again, for convex losses, as I said, ensembles are getting better all the time. So let's see why this is the case. Well, essentially, this is really just going to be Jensen's inequality and playing around with Jensen's inequality. So let's formalize the problem. Okay, so my formalization of the problem is going to go that way. So I have a bunch of predictions, y1 to yk. And for instance, they could be the probabilities of k neural nets for a single given image. So most of my, pretty much everything I'm going to say is going to be true for a single prediction. But of course, if we want to look at not a single prediction, not more than one, we can just average the results. And if you average monotonic curves, you will still have a monotonic curve, so that's not a big deal. But typically, you can really think of those y's are just the prediction of a single image. And what we want to look at is the average prediction, right? So the behavior of the average prediction, which is 1 over k times the sum of the k predictions. And again, since I assume that my models are just slight variations of the same model, it makes sense to just use 1 over k and not use weights because I assume that all my models are a priori equally good. I also assume that I have a loss function that goes from C to R, and again, C is a set where my prediction lives, which I assume to be convex, which is not a big assumption. We can just if it's not convex, like for example, if it's discrete, we can just use its convexel. And of course, we need convexity because we need this to be well defined. And the loss function depends only on the prediction because, again, since I'm looking at a single prediction, sorry, at a single x, a single example, well, the dependency of the loss on x and y and the true y, I mean, will stay implicit because the only thing that matters at this stage is the dependency on the prediction. So that's why I'm only looking at the loss as a function of just the prediction and nothing else, because all the other things I assume to be fixed. Okay, so really all what I'm doing is looking at a single prediction with a single true label, and but I'm not making the dependency on x and y explicit because because I assume that it's fixed. Okay, so I'm going to make one strong assumption that the y's, my prediction, the y hats are exchangeable. By exchangeable, I mean that if I switch the order, I don't change the distribution of the y's. In particular, this is a slightly weaker assumption than AID. So if you don't know what exchangeable means, you can just think of them as IID. So, and that's where, so this assumption is true for a lot of models, like again, random forest, deep ensembles, Monte Carlo dropout, because all the trainings are independent. But this assumption is going to be false where there is some dependency between the trainings. So for instance, for boosting. But again, I don't really care about those models today. I just care about slight variations of the same models, and those slight variations are very, very weakly dependent or even independent. Okay, and again, a super important object is going to be the average behavior of the ensemble or the behavior of the infinite ensemble. And this infinite ensemble is just the average of the prediction and essentially the limit of this finite average when k goes to infinity. And again, all of that is true for random forest, deep ensembles, bagging, so it's fairly mild. And essentially, as I mentioned, all of that are just going to be just variations of Jensen's inequality, and it makes sense, right? Because Jensen's inequality is like the main tool when we want to play around with inequalities, convexities, and average. Okay, so just a refresher about Jensen, because I always getting in the wrong sense, so it's also a refresher for myself, I guess. Jensen say that if f is convex, the f of the expectation is smaller than the expectation of f. And in particular, it's very useful in this finite form where f of an empirical mean is smaller than the empirical mean of the f of x's. And well, if we just use that directly on the predictions, well, we get that, and use the fact that the loss is convex. Well, the finite version of Jensen just give that the loss of the ensemble is smaller than the finite average of the loss of the individual models. So a direct application of Jensen says that well, the ensemble will be better than the average loss of the individual models, which is already quite good. This is already like some sort of collective intelligence result. And we could also just bound this average by the max and say that, okay, so the loss of the ensemble is better than the average loss of the individuals, which is also in turn better than the maximum, than the worst possible loss. Of course, this is like very, very basic and not new, and many people have discussed that starting probably from the 70s. And one thing I really like about this is that this is true, even we don't even have to assume anything like this is true even when the y's are not random variables. So here I'm not using IIT or actionability or anything. This is always true. And this is, I think, a very, very basic argument for ensembles that we can use in teaching, for instance, because it's very elementary math, and this is very nice. Okay, so if we further use the fact that we do have random variables, well, we can use the fact that the infinite ensemble is well defined, but again, another consequence of Jensen is that the loss of the infinite ensemble is smaller than the loss of the finite ones. Okay, so if we kind of summarize, well, that the loss of the infinite ensemble is better than the loss of any finite one, which is in turn better of individual models. But this says nothing about how to compare two different ensembles of two different finite sizes. And again, the arguments of the previous slides have been used in many papers, and you can find them in particular a lot in the 90s ensembles papers. I've put a few references there. and one other way to say that is just to say that this is just variance reduction. And indeed, if you say that L is just the squared error, this is just the standard variance reduction. Okay, so again, the summary is that the infinite ensemble is better than the finite ones, and the individual ones are worse than that as well. But here, what I want to ask is, if we take two different models, one of K models and one of K minus one models, which one is better? And actually, it turns out that we can also answer this question using Jensen's inequality very easily. And we can show actually that with Jensen's inequality very easily. And essentially, this just says that the average loss of an ensemble of K models is better than the average loss of an ensemble of K minus one models. And okay, so how to prove that? So I'm a bit late, so I'm going to be very quick here. You can take a look at the paper if we want to see the proof in more details. But the proof is very simple, so I do want to spend maybe 2 minutes on it. So okay, so here we want to use Jensen to prove this inequality, and okay, so Jensen is good to switch convex losses and expectation, and so we would, if we want to prove that, we would want to write y bar k as some sort of expectation of y bar k minus 1. The issue is that, well, actually no issue. It's actually not too hard to do it. Just using this formula, because the average of k numbers is just the average of the averages of the leave one outs. So by leave one outs, I mean if you average all numbers, all predictions except the J1. So you have k different leave one outs, one for each J that you leave out. So if you average all those leave one outs of k minus one models, you get exactly the average of k. And so if you apply if you apply Jensen to this, well, you get exactly that the loss of k models is smaller than the average loss of k minus one models. So here I'm not even assuming at this stage that the y's are random variables, but if I further use the fact that they are random variables, I can integrate on both sides, use exchangeability, and finally get that the loss is going down. And so essentially this is very neat, because this really proves that all those curves that were going down for the cross entropy, well, they're actually going down in theory and not just in practice. And this really explains all the results from the Probst and Boulestek's paper, and also the results from many deep learning papers on deep ensembles and Monte Carlo dropout. A few comments. It's possible to have strict monotonicity when the loss is strongly convex. This result, of course, from a mathematical perspective, is not new. The earliest version we found is from 1965 already. And we can find variants of this result in many contexts and fields. So for specific losses, it was published in particular by Probst and Boulestek, in particular for the MSc, but without just such a clean proof with Jensen, and without this understanding of the importance of the crucial role of convexity. If you're familiar with important Witty autoencoders, which are like some sort of VAEs, essentially the same proof was used to show that partial bounds of important Witty autoencoders are monotonic. And it was also used in an ensemble context when L is the log loss, actually, by this paper. So again, it's not really, nothing here is very new, but just perhaps what is new is the realization that this explains a lot of results for ensembling in a very general manner, and not just for the MSc or the log loss, but it's really just the convexity. Okay, so this was like the convex picture, again, very clean, very simple, like 2 lines proof. Everything is very nice. Unfortunately, this is not the case for the non-convex world. And as we saw before, well, ensembles can get worse. And of course, well, there is a very basic case where ensembles get worse, and it's the case where the loss is concave. If you assume that the loss is concave, well, the same reasoning as before will tell you that ensembles will keep getting worse. Of course, this is nonsensical, because I don't think I've ever seen a single concave loss in machine learning. I think concave loss don't make sense. Perhaps somewhere in economics, but yeah. But still, there is some insight to gain from this kind of nonsensical result. And the insight is that if the loss is locally concave, well, then we can expect ensembles to degrade the results. And okay, so do we have locally concave losses? Well, the question is, do we have non-convex losses? And if we look at the non-convex losses that are used in practice, well, often they have some non-convex parts. So for instance, here we have like 3 non-convex losses for binary classification. So the first one is the most important one, which is like the only non-convex loss that's used a lot, which is the classification error. Right, 0 below here the true label is 0, so the classification is 0 when we are smaller than 50%, and 1 when we're higher than 50%. And typically for binary classification, the other non-convex losses that are used, they are like some sort of smooth approximations of the classification error. And typically they are convex when the classification error is 0, and concave locally when the classification error is 1, or at least when it's when the prediction is wrong. And that's exactly the case for the sigmoid loss, which is really just a smooth approximation of the classification error. That's also the case for the spherical scoring rule, which is like a slightly popular scoring rule that is convex when the label is right, and concave when the label is wrong. And essentially, like all of those smooth losses, well, we have this neat thing that there are somewhere convex, somewhere concave, but in general, in a heuristic manner, they are convex when the prediction is right. So in that here on the left, on the right, sorry, on the left here, and concave when the prediction is wrong here on the right. Okay, so and the classification error is not smooth. So that in the classification error, this idea of local convexity doesn't really make sense. But I mean, it can be smoothly approximated by the sigmoid loss, so we can probably expect that it will behave like it. And typically the sigmoid loss in practice behaves a lot like the classification error. You have the loss for the sigmoid loss, and again for the correctly classified images, the loss goes down, and for the incorrect ones, the loss goes slightly up. So essentially the same sort of behavior, at least qualitatively, as for the classification error. We have similar stuff for regression, so I'm late, so I won't really discuss it, but for regression, it's the same thing. Non-convex losses, typically, they include 2 regimes. One regime where the loss is locally convex and the predictions are good, and one regime where the loss is locally concave and the predictions are bad. Here you have 3 losses that are used in robust regression, for instance. And again, empirically, I mentioned it already, but ensembles get better when the individual models are good, which was the case, let's say, for Ghost in the Shell, which was a movie that was extremely well predicted by raters, but it was not the case for John Wick 2, which was very poorly predicted by raters. And we can see that for non-convex losses, the loss goes down for Ghost in the Shell, and the loss goes up for John Wick 2. So essentially, ensembles get better for good points and worse for bad points. Okay, so can we try to prove that? And well, actually, we can formalize it. And for smooth losses, it's relatively straightforward. And we have this result that says that, okay, so if the infinite ensemble end up in the convex part of the loss, well, then the ensemble is going to be eventually getting better. And on the other hand, if we end up in the concave part of the loss, then the ensemble is going to be getting worse. And again, this is just a formulation of this idea that the convex part is the good part and the concave part is the bad part, because the convex part will be the part where the ensemble get better, and the one where the ensembles get worse. And the proof is essentially like a big Taylor approximation thing, because we have to go up to order 5, which is kind of a pain. And we do have to go up to order 5 because monotonicity is a high order phenomenon, and if we go to order 5, you can't prove monotonicity, and you can even find counterexamples. Okay, so this was for smooth losses, but unfortunately, like non-convex smooth losses are barely used. The only real non-convex loss used all the time is the classification error. That's of course not smooth, and here I have to assume that I have partial derivatives of order up to 5. So that clearly this result does not apply. But we do have like essentially. So I'm going to go to I'm going to a bit faster because I'm late. But we have essentially the same results for the classification error as well, and the result goes that way. If the predict is the same sort of thing, where what matters is the asymptotic prediction, so the prediction of the infinite ensemble. If the prediction of the infinite ensemble is right, and some additional assumption that I call weird assumption 1, but there are like quite technical assumptions about the distribution of the y's. Well, if the prediction is asymptotically correct, then the ensemble is eventually getting better. And on the other hand, if the prediction is asymptotically completely incorrect, which essentially says that the true label has the highest probability. Sorry, the true label has the lowest probability. Then the ensemble is eventually getting worse, not better. There is a big typo here. Worse. Yeah, big typo. Okay, and here the proof. So we can't use Taylor expansions because the loss is not smooth. We have to use large deviation theorems, and the kind of pain is that standard large deviation theorems don't work. We have to use strong large deviation theorems like Bahadur-Hangarao. But it works fairly well. The issue is that we have very weird regularity conditions. And in particular, well, those regularity conditions forbid some very, very simple ensembles. And there is one very weird counterexample that I found very fascinating. And that's an example that as I mentioned in the very beginning of the talk, it's the counterexample that dates back to Condorcet in the 18th century. The counterexample is this one. So we have binary classification with true label 0, and the average error is just the probability of being above 0.5. And if we have an ensemble of models that are just Bernoulli, so my models are just discrete predictions, well, one thing we would like is that the ensemble is getting better if the infinite distribution, so the parameter of my Bernoulli, so the infinite distribution, the infinite ensemble is right, and getting worse if the infinite ensemble is wrong. Unfortunately, you have an example here where the infinite ensemble is right because infinite ensemble is 40%, and so it's smaller than 50%, so it's like zero error. If you look at the loss, okay, it looks like it's going down, of course, and it converges to 0, but not in a monotonic manner. It kind of ping pongs like this, and you can actually prove, and people have done that actually before us in the 90s. There was a result about this, that this curve is never monotonic, never. And this is due to the fact that if you average discrete numbers like this, you can have ties, and ties are wrong because by definition here, my tiebreaker is that a tie is wrong. And because of the ties, it will never. And again, the probability of ties gets very, very small when k is big. So I think it makes it's very counterintuitive, but yeah. So we have this counterexample that illustrates that we need quite strong regularity conditions for this result to be true, and those strong regularity conditions come from those strong large deviation theorems. And to prove that, essentially, we had to prove that the tail probabilities of empirical means are monotonic. And again, we proved that using strong large deviation theorems. And the result is somewhat clean for binary classification, but I'm not even showing the one for multiclass because it's really not clean at all. Okay, so again, I'm late, so I want to conclude very quickly. So yeah, typically ensemble size, but I think the conclusion of our paper is the same as the one from the Probst and Boulez-Jemer paper. ensemble size should not really be tuned, and ensemble should be as large as possible. At least that's always true for convex loss, and for non-convex loss, it's true for, if your model is good, it's going to be true for most of the points. I also want to stress like a very strong limitation of our study, which is that we just essentially looked at the pure variance reduction effect of very generic ensembles. And this is a quite small part of the story. And specific kinds of ensembles should also have like specific theories. And I've just hidden like a few papers for specific theories for specific ensembles. And I think that's also very, very important. But that's something that we did not do at all. And in terms of future work, we are currently working on the ensembles of diffusion models. And so I was actually going to add those to the slide, but since I had the wrong time, I did not have the time to do it. But if you want to look at those papers and ensembles of diffusion models, you can take a look at my webpage, and they are very recent, so they will be easy to find. Thanks again, and sorry for the misunderstanding about the timing.
Great. Let's thank Pierre-Alexandre again. That was an excellent talk. Thank you, Pierre. We can take questions now. So if anybody has a question, they can come off mute and ask it, or you can also raise your hand. Okay, so I'll start then. I just wanted to clarify, for the convex case, these bounds are very nice and they just follow from Jensen's, that you can show this monotonicity. And I'm assuming it's the exact same way for the purely concave case, right? So if you have this,
Yeah.
I forgot what it was called, this particular V-shaped loss, then in that
Yeah.
setting, it's also very nice. So really like the brunt of the mathematical theory is improving what happens on loss functions that are first concave and then convex, right?
Yeah.
Convex and then concave.
Yeah.
I see. One of the things that I was wondering is that, you get these plateaus as you'd expect. Is there any theory that tells you about what those values might be?
You mean the limits of the like at what essentially like what yeah of
Yeah, at what
yeah
plateau would they
yeah
actually reach between and
yeah
stuff?
so of course I mean in that picture the answer is fairly simple because we divided the dataset in by looking at the actual value of the limits. So here on the left the limit is 100% and on the
Mm.
right it's 0%. But that's not really saying much. Yeah, so people have looked at that. So there is one issue, which is that what all our theory was about individual data points. And I don't think it's really interesting to look at the limit for individual data points because so for the classification error, it's going to be either 0 or 1, depending on if you're right or not.
Yeah.
And for the cross-copy also, I mean, you don't really care about the limit of the cross-copy for a single data point. But some people have looked at that for like at the average limit over the whole test sets. And there are like some quite nice papers. So people have looked at that theoretically. And here I think it's kind of important to assume that to assume some sort of stronger assumptions on the nature of the ensemble. And typically the tools that were used theoretically were similar to the large aviation that we use. It was tools like Edgeworth expansions, stuff like that. You have to use like kind of higher order tools, but I mean you can have very very nice results where you look at the at the at the yeah, but I think it makes more sense to look at the average of the plateau over the whole test set. So you have papers by so we do cite them in the paper, and they are super nice papers. You have papers by Richard Samworth about this for random subspace models, where you essentially it's different random subspace that give you the different predictions. You also have papers by someone called Miles Lopez about this. We also cite them, and they're very nice. But yeah, the nice thing that the tools are very similar to the ones we use, at least because they the classification error and not at other things, I think. But yeah, the tools are essentially also like those high order expansions of the classification error. Yeah.
I see. Thank you. Um, are there other questions? Okay, I have one more then. How significantly do you think that kind of averaging affects these results? So, you can choose the best predictor of these outputs, or you could also, do some sort of a aggregation that is weighted.
Yeah.
Um, so, do you think that would drastically affect these types of theories on the monotonicity of the loss?
Yeah, so that's a very good question. So that's something that we thought about a bit. The issue is that what we do is that we do assume that we do have to assume that the loss the ensembles are exchangeable to make sure that all those. So here we have a loss of we have this sorry, an average of losses of k minus one models.
Hmm.
And then this is true for any sort of number. So regardless of the dependency, and you could have a weighted version of this. It would be a bit nasty, but you could have a weighted version of this. But yeah, the issue is that so yeah, we do have to assume some sort of exchangeability to make sure that all those elements of the sum are equal on average.
Hmm.
If the models are different, then they are not equal on average, and then it makes a lot of sense to actually use different weights. Uh, but the issue is that our theory, I don't think our theory can. It's easy to expand our theory to that case. So I think in the convex case, you will always be able to find things like that are true. And again, I think one very neat thing is that so this thing that's super simple. This
Hmm.
is true in any case, right? If you replace the 1/k by some weights, this is also true. Yeah. Uh, so this is very neat, and you will always be able to find. I think Jensen is is going to give you arguments for ensembling for any kind of ensembling,
Yeah.
not just. And you can find people have used in Bayesian model averaging papers. People have used Jensen as well, so it's not really. So in the convex case, I think Jensen will give you something, perhaps something much weaker than what we saw before, but still something in the convex case. In the non-convex case, I think things become much more complicated, so I don't know. But I guess it would be possible to use, like, again, some sort of stronger deviation theorems for, I don't know, like correlation random variables or something like this. I think it's probably possible. I think you will probably get, so already the regularity conditions are a bit nasty. I think the regularity conditions are going to be even nastier, but I'm again, it's probably possible to derive something. Yes.
Okay. Thank you so much.
Thanks.
So if there's no more questions, we can thank Pierre-Alexandre again for this excellent talk. And of course, you can reach out after the talk too. Um, Perfect. Thank you so much.
Thank you.
Bye.
Thank you. Have a nice day.